Hey everyone, and welcome to our next session. I'm happy to have here Signe Riemer-Sørensen, and she's a senior researcher and research manager at Syntef Digital. And I just realized I forgot to ask how to pronounce the name of that place. But I am very excited that you're gonna talk today about the greener logistics with AI. So please take it away, Signe.
Thank you very much, Galina. And thank you very much for the invitation. Today's event is quite green in terms of logistics, since most of us didn't have to travel anywhere to get here. But most of our daily lives involve some aspects of moving either ourselves or some other stuff around. And all of this moving around generates CO2. The question is if we can use data and new technology to reduce this emission. So I'm privileged to work as a researcher at Syntef. For those of you not familiar with Syntef, it's one of Europe's largest independent research organizations. And in this case, independent means that we're not funded by the public system like a university, or we're not funded by any big companies like Google or anything like that. Most of our research, or most of our work, is funded through open calls from the Research Council of Norway or from the European Union, which we apply for in collaboration with industry. We are roughly 2,000 employees doing applied research under the vision of technology for a better society. And this better society, of course, we often map that in terms of the UN Sustainable Development Goals. We have 6 main institutes covering different areas. There's energy research, cover everything from hydropower planning and wind farm technology to electricity grid optimization, etc. We have ocean, everything from oil rises to autonomous ships and sustainable fish farming. We have industry, which is mainly the process industry and oil industry. Then we have manufacturing, which is adapting production of all sorts of stuff. Then we have community, which is buildings, infrastructure, mobility. And then we have Syntef Digital, which I'm working for, which is more generic, and we work with applications across all the other sectors. These institutes, of course, also reflected in the goals that we actually, in the Sustainable Development Goals that we actually perform towards. You see that there's definitely not an equal distribution. We contribute a lot more to affordable energy and clean energy or industry and innovation than some of the other ones. Today, we're going to focus on climate action and CO2 emission. And here it becomes exciting. Because where does Norway's CO2 come from? Now we're going to try and do a poll. I'm just going to activate it. It's going to be in the side next to where your questions are. I'm also going to see if I can show it on screen here. So go ahead and vote. I'll give you a moment to find out where it is. See some votes coming in. So no one think that we use any CO2 emission or emit any CO2 on energy supply and heating. Ah, there was one there. Good. I'm going to give you another moment to vote. Okay, you can keep voting if you want. I'm gonna leave it open here. But I'm gonna switch back to my slides and we can have a look at what the actual result is. Here it looks like oil and gas would be a winner, followed by manufacturing and agriculture. Let's have a look. So oil and gas is definitely our primary single source, but logistics is a serious contributor too, and it might even be the biggest one if we consider both road traffic, aviation, and motor equipment. If we consider everything under one and call it logistics, then it goes on top. And of course, since we include aviation, some reduction can be achieved if we just change our habits, perform fewer flights and less traveling. But a large fraction actually comes from transportation of goods. And I guess we all appreciate the selection in the grocery store. A classical way of applying data science and machine learning in climate modeling is to map CO2 emission and create models. They can be very useful to predict what happens if. And that's good for the decision makers and the policy makers. But the methods can also be exploited for direct CO2 emission. And there are two ways that we can use data-driven methods for direct CO2 emission, or direct CO2 reduction. One is that we can map where there is a potential for savings, and the other is we can actually optimize processes so that we waste less resources, and that we can map back into CO2. Let's have a look at some concrete examples. And you were pretty good at finding the poll, so I'm just going to go back here. I'm going to activate the next poll, because you are going to decide which examples you want to hear, at least which one you want to hear first. So you get, let's say, 50 seconds to vote. There are three options. One is reducing CO2 emission from road construction. One is better routes for last mile delivery. And one is stacking pallets for efficient transportation. And I mean, of course, road construction, that involves huge machines. That's pretty cool just by itself. Better routes for last mile delivery. I mean, who hasn't ordered anything online recently? And stacking pallets, that's a cute little robot. So they're all good. But it looks like the last mile delivery is winning here. So, okay, I'm going to close this one. Then I'm going to go back to the slides. Oh, I have to remove it here. Yeah, it did. Good. And then I'm going to swap over there. So, how many times a week do you get a package delivered? Well, e-commerce, the name that we give online trading, has exploded over the last years. Increasing number of deliveries from distribution warehouses to the doorstep. And that also means increased heavy traffic in residential areas. The distributors, they wish to use smaller and more sustainable means of transportation. That can be either by foot, by bike, electric bikes, etc. But that also requires navigation on a completely different scale than before. And for that, we need better maps. Try to have a look at this area and imagine that you want to go from A to B. Well, with the current map, you might be sent on a route like this, while this might actually be the shortest route if you're on foot and you can take all the shortcuts. So in this particular project, we use deep learning models to update the maps. And of course, not just the maps, but actually the underlying graphs that defines what the maps look like and are the ones that we can actually do route planning on. And we update them with new routes and paths based on satellite data. So basically learning how does these paths look like. And that's in particular useful in new residential areas, but it turns out also that even in existing areas, you may be able to identify new shortcuts. And of course, if we think a little bit ahead in the future, and we imagine autonomous delivery vehicles without a driver, this kind of navigation information also is crucial. Okay, you'll get to hear about the other examples as well. So reducing CO2 emission from road construction. 1.5% of Norway's CO2 emission comes from construction machines. That's quite a lot. In this project called Data-Driven Sites, it's a project we have with Skanska Norway to reduce CO2 emission, cost, and time for road construction. And Skanska, they have mapped that their machines, they're idling about 50% of the time. So that means they're standing with their engines turned on about 50% of the time that they're working on a project. Here we have already excluded all the time that they are in service or anything else, the time when they're working on a project. So the objective of the project is to reduce this idling by around 10%, which will reduce fuel consumption and CO2 emission by roughly 5%. So in order to do this, we want to build an optimization algorithm for real-time task allocation for dumbbells. And dumbbells, that's these big machines that transports rocks, gravel, soil, whatever, during the construction. In order to have this optimization algorithm, we need a description of the construction site. And naturally, this construction site is changing over time. I mean, they're building a road, right? It should change over time. But consequently, we also need some way of dynamically mapping it. Here we are lucky that Skanska, they have equipped all their machines with iPads. Not because of us, but because they can use the iPads to communicate with the drivers, and the drivers use the iPads to communicate what they have been transporting, and that's how they're being paid. So it's very important for them. But we can exploit these iPads and get GPS data. And then we can use a combination of unsupervised learning and a couple of other methods to generate maps that can be utilized in the optimization. And this we are proof of concepting at the moment. We're testing a proof of concept. We also need to optimize for minimum fuel consumption, not just time or distance. So we're building a supervised learning model to estimate fuel consumption during various activities. And in order to do this, we've outfitted a couple of these big machines. That one is actually a CAT machine, and this Volvo machines that we have that we're working with. But we've outfitted them with high-resolution fuel loggers. And if we're combining those data with GPS data, it allows us to model the fuel consumption against driving patterns. And this is the only dataset in the world with this kind of resolution on actual usage of dumbbells. And the first preliminary result was super exciting. It showed us that dumbbells are using fuel while driving. Okay, that was trivial. But it also showed that the relations are complicated. They're not trivial. And it seems like consumption is very sensitive to uphills. So it may be worth planning your site, your construction site, with as flat transportation as possible, maybe increase use of diggers or maybe increase use of conveyor belts on the construction sites. And when this analysis is finished, we hope that it can be implemented in the tools that are currently used for budgeting CO2 emission from large projects, which is a requirement when issuing these large road projects. Of course, data has been crucial for this project. However, the project has also significantly benefited from taking out smaller results along the way and setting them in production. And several of them are just very simple from an analysis perspective. It's almost pure data visualization. But they now provide data-driven support for the day-to-day decisions on the construction site. And that, in turn, has contributed to transform the way that Skanska internally think about their data and the people out on the construction sites think about the data. So now they're putting a lot more effort into collecting useful data or collecting high-quality data because they can see that it informs them. So, for the last example, when you raid your local shop for dinner, you rarely have time to think about the complexity of getting such a large number of goods efficiently distributed across the globe and ending up right in front of you. Maybe you should, maybe you will next time you go to the shop. Here, I'm only going to talk about the last step before the shops, namely the wholesale warehouses. The goods, they're coming from the manufacturers on pallets with only one type of goods. Or maybe a couple, but in principle, just think about it as being one type. And then they have to be distributed to individual shops according to demand. And this requires what we call repalletization or repacking of pallets. And today, this is hard, unattractive human labor. So we're working with a small company called Solver that are working on building a robot to replace humans. However, the current robots, they are not able to stack the orders to the same quality as humans. So if we were to replace the humans in the warehouse with these robots, that would increase the number of pallets needed to restack the goods, which would again increase the CO2 emission from further transportation. And just to give you an idea of the numbers, every week, ASKO, which is the main distributor in Norway, they distribute around 100,000 pallets. This is done by putting an average 30 pallets into a truck and then driving to the customer. So that will say that we have more than 3,000 truckloads of pallets every week, only in Norway. So if we could do a more efficient stacking, that would contribute to fewer truckloads and hence less CO2 emission from transporting the goods from the warehouse to the customer. And let's say that we could increase the capacity, so how close we can put the boxes together or how much space the box is taking up, by 5%. If that could translate into to truckloads, it's not direct translation because there's something with form factor as well. But let's just imagine that it could translate directly. that would be 200 fewer truckloads every week. That's quite a lot. But in order to do that, we need better algorithms. Humans, they're really good at recognizing patterns and solving puzzles. Robots are not so good at that. So initially, you may think that this is just a 3D Tetris, and something that we've heard about games today, something that AlphaGo or similar AIs, they could easily learn to do. Well, the challenge here is that the score is very, very different. Instead of getting rewards for just placing boxes in a specific pattern or similar boxes close to each other, you're scored by several criteria. One thing is, of course, that we want the stacks to be compact. But they also have to be stable. Not just stable in themselves, they have to be stable during the stacking, even when you add additional boxes on top of them, and when you start driving around with this pallet. So you also have to be able to sort of shake the pallet and still leave them stable. In addition, there has to be a feasible solution. And here, by feasible, I mean that we need an algorithm that can actually put all the boxes onto the pallet. And the boxes must also be possible to place for the robot, because it has this arm, and of course, you can't place boxes that go on top. You can't place in the beginning. You have to place boxes from bottom up. So this becomes a multi-objective optimization problem that's really hard to solve. And now we haven't even talked about non-square boxes or the interconnection with other optimization problems, because the receivers, the shops, they want to unpack in a specific order. We also have to think about the shortest driving path through the warehouse for the robot. And that means that we should also start thinking about the warehouse layout. And that means we also have to start thinking about, what about when they're coming in with the pallets? What is the optimal path for them? So there's a lot of interconnected problems here. And that means that the entire problem that we want to optimize become huge. And that calls for stronger and stronger optimization algorithms. Here, the approach is that we first start to use machine learning to help a classic optimization algorithm to become faster. For instance, by learning what an unstable stack looks like very early in the stacking. So instead of having to compute the stability every single time, which is expensive, then we can just do a very quick prediction saying, does this one look like something that will become stable in the end? So that's what we can do for stacking boxes. But artificial intelligence also generates CO2. So let's try to get a perspective on how much CO2. We're going to go back to the polls. Just going to activate the last poll. Here. It is now published and showing on screen. So what does the CO2 emitted during training of a large language model correspond to? Any ideas? Does it correspond to flying 12 times around the world? Drive a truck 10 times around the world? Drive a motorbike 10 times around the world? Or sailing a sailboat 5 times around the world? A couple of suggestions here. A couple of more seconds to vote. I'm gonna leave it up. You can keep voting if you want. Looks like most people think there's a lot of CO2 in training language models. Let me find the correct answer. So, large language models, they use electricity equivalent to approximately 300,000 kilos of CO2, which corresponds to a standard delivery truck driving around the Earth at equator more than 10 times. So, in logistics, the problem complexity is large, but the challenge is they're computationally heavy rather than data heavy. And that means that we can actually do improvements with much smaller models trained on regular desktops or even laptops. And they will lead to positive sustainability effects. So it is easier to provide improvements within logistics than it is with language models. The mobility and the logistics sectors, they have very large emissions, and they have very large potential for reductions. but it all hinges on the ability to model these complex relationships. And that we've written in something about in this paper that's quoted on this page. So data-driven methods and machine learning, they're already paving the way in some fields, and they will, without doubt, be crucial to provide models enabling large reduction initiatives in these sectors in the near future. And these changes are imperative because the global society faces tremendous challenges in terms of climate and biodiversity. So many industries, they can become greener by reducing waste or using their resources more efficiently. And this requires a good understanding and a good modeling of the system. In addition, another benefit is that there's usually an economical upside as well. If you waste less, you waste less money. So there should also be a business perspective to this. The big question is, does it actually matter? Shouldn't we just transport less stuff in general? We need to reduce the demand for transportation rather than just the CO2 emission from the transportation. But on the other hand, the question is, how much are you willing to give up? And unfortunately, these are not questions that can be answered by AI. They have to be answered by you and me. So thank you very much.
Hey Signe, thank you very much for your talk. And we have a few minutes for questions, but while the questions get assembled, I'm going to ask you my usual one. I would probably say. So I think that these topics are very important, but I think it's also interesting to talk about what actual technical methods are used for some of these optimization problems. So, if we could dig a little bit more into the type of algorithms or the type of technologies used. So I know, for example, that, we talked about GPT in the previous talk, and GPT is famously extremely, as you said, extremely expensive. But, it takes a little bit, where are the trade-offs? What kind of methods are used for automating some of the things that we discussed?
As I already mentioned in the first, in the second example on the dumbbells, we see that we actually quite often do not need very complicated methods. We can usually do with quite simple methods at this point because the potential for reduction is so large.
But which specific methods would you say? Can you give just a few examples?
I can give a few examples. In the dumper example, we use something as simple as k-means clustering when we're generating the maps. Okay. We do it by looking at where they're turning, and then we make some that'll become candidates on where do we have an intersection, because we basically just need to identify all the intersections. So they're candidates for intersection, and then we cluster all the GPS points that are coming in and out, and then we say if there's more than 2 clusters in a k-means clustering, then it's a crossing. Otherwise, if they're just 2, then it's just a bend on the road. So very simple method. For the let me just think. For the improving the maps, that's a standard pre-trained algorithm, which may be heavy, but it's not. We're using transfer learning, so we're using a pre-trained method. Basically, I can't remember the name of it, but you can probably Google. It's a lot of convolutions. For the stacking problem, we did make some attempts with reinforcement learning, but then we didn't succeed. It's more complicated than what you just think to set it up. And then we went back to an existing beam search algorithm, and instead decided to see what we could do to make that one faster based on machine learning, rather than which I think is actually also more interesting, because that's going to be much less computationally heavy than the full reinforcement learning agent.
Yeah, I've seen these problems before, for what it's worth, where reinforcement learning requires quite a bit of data a lot of the times, and
in this case, data would mean simulations. So data would mean that it's not even just data that you have, it's data that you have to generate first.
Yeah.
And that's why we went back to the beam search.
Yeah. I used to do computational geometry research, so I really appreciate that a lot of these very traditional things that we used to do 20 years ago are coming back. I think there are a lot of really good hardcore algorithms that could be improved on top of, maybe a little bit with machine learning, but I think
the crucial point here is that we don't necessarily always need to find the best solution. We need to find one that's good, and we need to find it fast. Yeah. And for that, machine learning is perfect, because we can't give any guarantees, but we can probably help speed up the process significantly.
Yeah. And the other problem is that, just from my old experience, is that if you look at it as an overall problem, it might be NP complete. And this is also another reason why it's better to apply machine learning, right?
Yes.
So that's kind of a fun thing. Right. We have a question, I think. What do you think is the most important step in a green project?
Oh, based on my experience, the most important step is realizing that you have a challenge, and setting your mind on doing something towards it, even though it might cost you. That was probably not what you wanted to hear. You probably wanted to hear that I said that, oh, data collection or analysis, or but what we've seen really is, and we've seen this with Skanska as well, that the data quality has significantly improved when they realized that data had a value. And they realized that data had a value because they had a problem that it turned out that we potentially could solve using data. So this realization that there's a value in your data.
Yeah. Yeah, very cool. Thank you very much, Signe.